Should we go? Okay. Go for it.
Cool. Hi, I'm Ella.
And I'm PY.
And we're both engineers at Square. Yeah.
Yeah.
And we spent a lot of time working on building a developer platform there. So we spent a lot of time this year dealing with spaghetti code. Who knows what spaghetti code is? Yeah.
I know.
I'm sure we've all dealt with it at one point or another. It's code that's really tangled together. And so we're going to talk today about how we've gone about detangling some of that spaghetti code at Square. So we're going to talk about why we're doing it, how we find pieces that we want to pull out, then how we actually pull out the pieces, and then how we keep our changes in place once we made them. So why are we doing this? Once upon a time, Square only had one product, right? You've probably all seen it. It's a little credit card reader that plugs into your phone and you take payments. But eventually, we built a whole suite of products around this. We have a whole point of sale app, which has a ton of functionality, things like invoices, item management, employee management, things that you don't want in every app. But we have a lot of really core functionality in these apps as well, right? Like, we can take payments. That's a core competency of Square, and that's something we want to reuse. So we might want to build other products on top of this functionality. For example, we recently released Square Register. This was actually released this week, and it's a 2-screen display. So you have a buyer-facing screen and a seller-facing screen. These are actually both running custom versions of Android. So we know we want to take payments with this app. Obviously, it's a point of sale. And we want to reuse a lot of the same code. The problem is that code is a lot of spaghetti, right? And so this is kind of the world as it is today at Square. So we start out with our point of sale app. We have one app. It depends on this giant spaghetti tangle of code. We do have some core modules extracted at the bottom here, like auth, encryption services, things that are nicely separated. So we wanted to think about how we can take this giant spaghetti block and reuse it. We want to build a bunch of other apps on top of the spaghetti. So we want to define a world in which this is an easy thing to do. So we want to get to a place like this. You can think of dependencies in this chart as kind of moving downwards, right? So everything's depending on the things below it, and it's forbidden for anything to depend on something upwards. So we start with our core modules at the bottom. These are things like HTTP and utilities, but also notably things that weren't in the diagram before, things like payments. Payments shouldn't be something that are tangled in with everything else. They should be an isolated core module. This allows the features on top to then depend on these core modules. So this allows us to have features like a payments SDK, for example, that would depend only on the payments core module and on other modules that it might need. Then at the top, we can build a bunch of different apps. And the key thing here is that these apps can pick and choose which features they want to include. So we don't want to have to include, for example, loyalty and onboarding in our third-party apps that want to build on top of a payments SDK that only need a payments core module. So this is cool. We kind of think this is how we want our code base to be organized at the end of the day. But the problem is that we are constantly shipping things. And we can't take time to just rewrite our whole code base from scratch. It's no one team's job to do a giant refactor. And as a result, the spaghetti is constantly growing, right? Teams are building features. Teams are making things. So we need to find a way to progress towards that nice diagram goal, but in an iterative way.
All right. So this is kind of where we are. And really, since we want to keep shipping, the next step to have several apps is to just add them on top and have everything use the same kind of spaghetti, right? So we could do that and ship and say it's good. We're done. We shipped the app. They're all using the same spaghetti, but it's fine. Is that okay?
I don't think so.
No, it's not, right? Not only because we also want to build SDKs, which means we need a nice API surface, but also because that spaghetti is really like this, right? And so the apps, they get bigger. They have a lot of unneeded code and resources. And so a big binary size is bad, but that's not the only problem. The problem is having a lot of code that is useless, is that you have a lot of complexity. It's really hard to understand, and that leads to a lot of bugs, a lot of unintended side effects, a lot of crashes. So someone will do a change in a part that your app doesn't care about, yet it's going to break your app in some unexpected ways. So that's not great. So we are here, and what we want to effectively do, and what we're going to be talking about today, is pulling code out of the spaghetti. So trying to create some more feature modules that are going to be maybe depending on the spaghetti on the core modules. And so by pulling up, and then also pulling down and creating core module. So And at the end of the day, we really want to be in that place where we can pick and choose and build an app that uses a part of the features and maybe a part of the core modules. So let's, we're going to focus on that. We're not going to talk about build speed, which turns out was the talk right before on this stage. So I invite you, if you haven't seen it, to watch it online. That's a whole other subject, and having more modules can, in some cases, and depending on the build technology, make things faster or make things slower. We're not going to talk about that.
Nope.
All right.
Cool. So the state of the world right now, we have all these apps that contain a lot of spaghetti code. So we want to pull some of the code out, but we're not really sure where we want to start. Hence our frowny face here. So we're going to start with a little bit of common sense, right? That's where we all like to start, and we think that we have it. For example, something like HTTP, that's going to be a common module, right? Because we're not going to build an app that doesn't need to send HTTP requests, probably. On the other hand, something like printing receipts is probably going to be a feature. All the apps don't need to know about the details of printing receipts. They might depend on a printing core module that we would want to extract down. That might all live in the hairball, we don't know. So that's fine, we can look at our stuff. But eventually we're going to want to turn to some real analysis. Otherwise, we're going to hit some problems.
Yeah.
Yeah, have we hit some problems with
With the manual approach?
Yeah.
We did.
Yeah.
Do you want to talk about static? Yeah.
Yeah, sure. So we can start looking at our code base without running anything to figure out what pieces we can pull out. And to do this, we looked at one of Jake's old blog posts from 2014. It talked about Google Play Services is a monolith. Basically what he did was used a tool called dgraph. This is an open source tool that lets you analyze your package and class dependencies within your project. So you basically write a config file, give it the jar for your app, and look at some really cool output. And what he found here is that there's a lot of packages in Google Play Services that are really grouped together. And you can kind of see these lines between packages, which means that maybe we should be able to split up this Google Play Services monolith into smaller pieces. And ideally, we could use the same tool like this and run it on our app and find some nice boundaries where we could cut ours as well. And Google Play Services did eventually do this. So we thought, cool, let's write a nice dgraph config file. So this is what we found with our app. I call it the Death Star. And this is what we tried to analyze all the packages separately. So you'll see that this is not the most useful thing in the world, but we took a step back, we tried again. So here we restricted it to only our main UI package. So this is config file on the left. We specified the output file, we give it our jar. We manually excluded some Dagger classes that get generated in the right package. And then, so the next block at the end is called lib, but that's just a slice of our code base. So we take the package after UI, put it in parens, that's a grouping. So that means that each of the nodes around the end of this circle are one of the packages following com square up UI. And there's a lot of different edges in this graph, but we can start to take a look into it. There's red edges and black edges. And so the red edges are things that dgraph has said violate dependency constraints. And you'll notice that we didn't actually specify any dependency constraints, but the default one is that there are no dependencies between packages. So there's no circular dependencies between packages, right? So if two things are linked with red, it means they're probably in a bad state for dependencies and they're dependent on each other. But those things will draw your eye first, right? So look at main and tender. So main is pretty much hard red connected to everything. We're not going to try to pull that out of our app first. Tender as well, right? That's something that's key for a payment. We support different tender types at Square. But we're probably not going to start pulling that out first because it's got red edges going out everywhere. But eventually the hope is that as we start pulling out more code, then these dependencies go away and we can start untangling this yarn. However, we see some other nodes which might look a little more promising. So there's an invoices UI package here, which has a lot of incoming and outgoing edges, and they're not all red. So maybe, for example, the spaghetti depends a lot on invoices, or maybe, in the better case, invoices depends a lot on our spaghetti code and not the other way around. So we could perhaps pull that up out of the spaghetti and make those potential features. But yeah, so we found some points that are kind of cool, but it's really not the most informational tool, especially if you don't have really well-organized packages, which I'm sure all of you do. But the more disorganized your code base is, the less useful static analysis tools are going to be.
So in general, we found that to not be super helpful, but there is one case where we found it actually really, really helpful. As we started looking at the different groups that we are seeing, we noticed one thing that were standing out, and that's libraries. Every single library that we were using was like nicely packaged in its own corner, and we realized this is actually really good at identifying libraries, but the reason is libraries have to stand on their own. They already exist in their own world, and they're already decoupled from your app, right? So that doesn't really tell you anything, but that gave us an idea. All right, libraries. Let's look at that. So there's this Gradle command, Gradle task that's basically dependencies, right? And when you run that, it gives you this output, or an output like this. And it basically tells you, for each of your app, the tree of dependencies. And so you might already think you know that from the dependencies you're adding, but in your build at Gradle, but this gives you the transitive dependencies as well, which is something that sometimes you don't realize you're pulling this or pulling that. So in our case, we're making all these apps that are depending on some shared code, and all of a sudden we're realizing, wait, I don't need a chart library in my app. Why do I have a chart library as a dependency, right? And so then we're going to start investigating and try to figure out why we're using that. So this is very interesting as a way to sort of scan and think, does this make sense? Is it okay for me to use this? Should we be using this? So as we saw, static analysis can be great if the code is already perfect and well organized. But if your code is kind of like spaghetti code, it's not going to be super helpful, or at least for us, and we maybe haven't found the way to make it helpful. So let's go back to how the world where we are. We build these apps on top of the spaghetti code. If you pause for a second, if we think, okay, what's in the spaghetti code? Well, it turns out all of the features and some of the core stuff is in there. It's just tangled, but it's already there, right? So when you're running an app that's using it, say I'm running this third-party app that's using this Pay SDK, it turns out that it's only going to exercise some of the code paths, the ones that are very visible here. So at runtime, my app is actually only using some of the code, right? And the rest of the code is not even loaded. It's just staying there dead. So that started to get us thinking. We can figure out which code, and that's the interesting part, that's the key part. We can figure out which code is live versus dead. So let's take an example. Or rather, let's take a step back and talk about the kind of codes that there are. We realized that there are kind of three kinds of codes. The first one is the one that's running. It's useful, it's great, we love it, it's doing the features. The second one is the dead code. It's the code that's just sitting there and doing nothing, and it's in your app because it's from some dependencies and you don't really need it. But there's a third kind of code. It's the code that's running but shouldn't be running. It's maybe like a background services. So we call that the zombie code. And what we want to do is we want to kill the zombies and also take out the dead code. So for example, that would be, think about a background service that's doing a database sync, but maybe you're never using the database, right? But it's just syncing every day or something. That's kind of useless. And so that's like zombie code. So all of that code is in one app, right? So how do we kill the zombie code? Well, it's pretty easy. You know how to do that. You can just hack it together. Just put a Boolean, this app, just don't do anything, right? And don't start the thing that you shouldn't be doing. It's not perfect and beautiful code, but it's a great way to turn zombie code, code that's running, into dead code, i.e. code that's just there and not useful, but not running. Another way to do that is to have alternate implementations that don't do anything. It's pretty much the same idea, but instead of using a hack if condition, you just have a different implementation. So we're here, and with these things, we can kill the zombies. So the zombies are dead now. And then we just have to figure out how to refactor that dead code out so that we just have the app. One thing to keep in mind, when I say dead code, I say dead from the perspective of the app running, and not dead from the perspective of code that you can delete. We're still talking about 2 or 3 apps using the same shared code base, right? So this app doesn't use that dead code, but that dead code is actually useful for that other app, right? So, your turn.
Yeah, so we have this belief that there's dead code in our app somewhere that we're not using. And the question is, how do we figure out which code is a dead code and which code is a live code? We could go back to our common sense, but that will only get us so far. So now we turn to some runtime analysis. And the idea here is that being Java developers, we know that the JVM is going to load classes only when we need them dynamically. So we think that we can find dead code by figuring out which classes are loaded and which classes aren't loaded. So our first attempt at doing this was this method here, print loaded classes. It promises to dump a list of all currently loaded classes to the log file. This is really cool, it's Android API 1. However, it did not work for us. So what we did was we played around with our app, called this method. We see a lot of output, but it turns out we know 3 classes are being loaded because we wrote the code. Looked for it, not there. We did see some Dagger factory methods that were associated with it, some of the inner classes being loaded, but not the classes that we knew we wanted. So we don't trust the output of this method. Best of luck to everybody else. Next, we tried this method. We got a tip from a friend that says, oh, just ask the class loader which class was loaded. So this is find loaded class. This is a class loader method. It's supposed to return the class if the loader has been recorded by the Java virtual machine as an initiating loader, otherwise null. So we're like, okay, we open the dex, we find a list of every single class in our app, and then we pass it to this method. We say find loaded class, and so we expect that if we get a null back from this, then the class wasn't loaded. The only problem is this was never ever returning null. So when we call this method, it actually triggers the class to be loaded.
Yep.
Yeah. So not super helpful. So we thought we might get some creativity up in here.
All right. So who's heard about Leak Canary before? A bunch of people in the audience. Great. So yeah, 2 years back, I open sourced this library, and I'm not going to go into describing what it does, but one of the interesting things about it is that it involves taking a heap dump and then parsing it to find some information in it. And as we were stuck on this, I realized, hold on, I've seen this before. In a heap dump, you know which classes are loaded. So what about we do the same trick? So we ripped out some code from Leak Canary and really just starting using headless Android heap analyzer, which is a library to parse heap dumps. And I'm going to walk you through the code because it's pretty simple. So once you've imported that library, the first thing we're doing is we're loading the heap. We're taking a heap dump. So we create a file. We dump the heap to the file system. Then we create a heap dump parser from and we basically parse the heap dump into a snapshot. That's just reasonably easy. It does everything for you. Then we wanted to find all classes that were loaded in memory. So there's a method, find all descendant classes. So we find all the subclasses of the object class. And as you know, the object class is a parent class of all classes in Java. So that gives us the list of classes that were loaded. Now there's a bit of a trick here. The first is we don't care about all classes. Some of them are the classes of the heap dump parser. So we don't want to know that we just loaded the classes for the heap dump parser. That's like noise we don't care about. But also the interesting bit is so the heap dump is going to contain all classes from our dex and also the classes from the Android SDK that were loaded. So at this point, we can differentiate. So we're going to put all of them in this loaded SDK class set, and then we'll sort of triage later. Interestingly, also, we are classifying by package. That's going to be nice because then later we can say, oh, there are like 1,000 classes in this package, and then we can start digging. I mean, it's kind of like a nice grouping for us to have. So what do we do next? Now, we have this list of loaded classes. So Android has an API that's pretty nice. It's called dexfile. It's deprecated. Let's just hope that they don't remove it because it's very useful. So you pass it the path of the APK. And it works with multi-dex, by the way. It's basically going to load it's not going to load the classes, but it's going to find all of the classes in the APK. So then you just iterate on it, and you just get the name of all classes in your APK. And so we sort of apply the same. We ignore if we don't care. So the goal here is to sort of like, we had this list of all classes that were loaded, including the Android SDK ones. We see, okay, I just found a class in the text. Is that class in the loaded classes? If yes, then I put it in the loaded class set. And if it's not loaded, I put it in a non-loaded class. And because I'm removing it from loaded SDK classes, in the end, in loaded SDK classes, you only get the SDK classes, I guess. So with this, doing this work. By the way, yeah, it's not a library. Maybe it should be, but I believe that you can actually code that yourself. It's not too hard. We get output like this, which gives us, and this could be a UI, a nice activity, but we just output it in the logs or in a file, and basically gives us, okay, this package has that number of loaded classes and then the list of classes, or that number of classes that were not loaded. And so that's super interesting for us, because if we look at all the classes that were loaded and we sort of like look through our packages, we might realize, hold on, this package that's about charts, I don't care about it. It shouldn't be loaded. There's no code exercising that. And so you can go, that's basically zombie code. And so you can go and find why is it loaded and then stop it from being loaded. And then there's the classes that were not loaded, and that's the dead code. It may be the dead code, actually, because when you're starting at first, you think, OK, I've gone throughout the entire app. I think everything is loaded. And then you look at the classes that were not loaded, and you realize, oh, I forgot about that use case. And so that kind of gives you more room for exploration and finding things that were not things that you haven't explored. And once you're done, you do it once again, and now you really have the list of everything that's loaded, everything that's not loaded, which is the dead code. And that's pretty nice. And so then with these numbers, we can prioritize. If a package has one class that's not loaded, I don't care. But maybe if one package has 1,000 classes that are dead, that's probably a good target to go and move out of the spaghetti.
Yeah. And another cool tool that we decided against using are code coverage libraries. And these are things that you can use in tests. I don't know how many people have used them before, but basically, yeah, you have. You run them in your test. And then afterwards, it tells you which lines of code were actually executed. It hooks into the debugger. So in this case, we ran the transaction request test, and we covered most of this builder method, but we forgot to check the case when our tender type's length was 0, so we never tested that we threw this exception. Probably works, but we wouldn't have known. And you can actually hook up these code coverage tools when you're not in a test. Just hook up the debugger to your app and just run it. The problem is that you have to stay connected to your app and hope you cover all the code paths, right? So you're going to open your app, connect one of these code coverage libraries, and try to click on as many buttons and do all the things, and then see the output at the end. But we found this a little bit too restrictive. And the nice thing about taking a heap dump is that it'll just build on itself. You know, the classes aren't going to become unloaded. So that's nice. Let's say we have a package that we want to pull out of our app. We have some code. We saw this add note screen runner over here at the top. Let's pull that out of our app. Let's use the new Android Studio modularize feature.
Quick question. Who's heard about that tool before? It was announced at Google I/O.
Yeah.
It was pretty exciting. I was super excited.
Yeah. So I grabbed 20 classes from this UI main and thought maybe I'll make those into their own module. And this is what happened. What you're going to want to do if you want to attempt to use this tool is click on the preview pane, because it's actually recursive and it'll show you all the dependencies of your class and then all the dependencies of those classes and so on and so on. You're probably going to want to just manually look at that and see where you want to break off the dependencies.
One thing I would add to that is the first time I did it, because I was really excited after Google I/O, I did it on one class. I probably picked the wrong class. It took 5 minutes to tell me anything, and then it was move, I think 8,000 classes just for that one class. And I was like, no.
Just do it over and over again. It's fine.
Yeah.
But we found this was a little bit too slow of an approach. So we move on to our next favorite tactic, which is just move some stuff and see what breaks. This is cool. We just take all the code we think was dead and we don't want in our app, and we move it out to a new module. We're going to get red squigglies everywhere after we F6 this, and we're going to see a bunch of errors, right? And some errors are because your feature is depending on the spaghetti code, and some errors are because the spaghetti code is depending on the feature. And sometimes it's really easy, right? You're going to take some things, you're like, oh, I see the feature's breaking because it needs something in the spaghetti code, but maybe that really belongs along in the feature. Or vice versa, maybe there's something in the spaghetti code that really should be its own core module. And that's extra work, but now you want to create a new module and have both libraries depend on that and clean things up. Sometimes that's not going to work out, and a lot of times there's still going to be some core code left over in your spaghetti once you extract the feature out, right? Because there's a lot of things in our spaghetti. For example, we still have some payments code in there. We're probably going to need that. So instead, at first, we don't break the dependency on spaghetti. So we pull out these features, and we just add little spaghetti dependencies there. So this way, it's only breaking in one direction, right? We're only breaking if there's a dependency of the spaghetti on the feature, and that's what we really care about disrupting here. And also, we're getting a win really quickly here, right? Because one of our main goals is to have all these apps at the top not need to require all these features. So once they don't depend on the spaghetti, they can depend on only the features that they need to include and nothing else. We're still getting the spaghetti at the end of the day, but at least third-party apps don't have to include an onboarding module or employee management. Cool, and the idea is that eventually the spaghetti is going to shrink down. Maybe it'll become its own core module at the end of the day, and it'll get easier and easier as we iterate and pull more things out. Yeah, so we have our feature module. We made it. It still depends on the spaghetti, but everything's okay. We're kind of okay with that. Now we can use the cool Android Studio dependencies feature to analyze where we're still depending on the spaghetti code. And this is a really cool feature. I don't know, how many of you have used this before? Yeah, not too many. You click Analyze Dependencies in your Android Studio.
That's really cool.
And you get this nice 3-pane layout here. So on the left, you see all your project modules. You can click on one of those. And then on the right panel, you see all of its dependencies. And then you can click on one of those, and you actually get all the different references in code where you're depending on something. So we created an onboarding feature module out of the hairball. And on the right, you can see some of our hairball packages. Then we can see this address layout that we're depending on. And maybe this is something that's actually shared between a bunch of different features and shouldn't be living in the spaghetti code. Maybe it should be its own core widgets module or something like that. And we can break more and more of these, so eventually the feature doesn't have to depend on the spaghetti at all. Cool.
And one thing I think we wanted to mention is that, so this works great once you've done the work and you want to see how you decouple from this shared module. The one place where it sadly doesn't help is when you have this code and you want to extract something that's going to still depend on it, and you're like, okay, this add node screen, what depends on it? Like, how can I move it? So it's basically a backward dependency. So that screen that we just showed you doesn't help, but Android Studio or IntelliJ has another one which is called backward dependencies, which sounds pretty great because that's exactly what we want. The problem is we could never figure out how to make it work. It always shows test, and I don't understand why. If someone knows how to do it, I'd love to talk with you, but we just couldn't use that either.
Yeah, not super helpful. You can, option F7 on an individual class, but when you're working with a package, backwards dependencies are a little bit difficult.
Tricky.
Yeah. So we pulled it out into its own module, right? It's still depending on the spaghetti. Maybe that still doesn't quite compile because the spaghetti has some dependencies on the features that maybe it really shouldn't. So this is where we turn to decoupling our code. We're going to start with extracting interfaces out. So this we know is dead code, is never running. This is actually pretty convenient because this add note screen and all of its other classes are started via this add note screen runner. And it's only got one method, which is start in the note screen. This is real code from our app. Go to note screen. So we're going to turn this into a new interface, and we're going to call it the add note screen runner. We're going to keep this interface in the spaghetti and put the real implementation up in the feature module. So we're going to create this real one. We have a not supported implementation there. So that's what we're going to include in all the apps where this code shouldn't actually ever be running, right? We have all this dead code. This is its replacement. And we're going to make sure to throw if we ever try to execute this code, because we want to enforce that it's dead if we think it's dead. Then in our app components, we start binding everything together. So here, this is a component for one of our apps. We call this the SDK app. And so this one doesn't want to ever go to the add node screen runner because we found that was dead code. So in our module, we're just going to provide it here. We're going to bind it to the not supported implementation. Then in our real app component module, the one where we actually want this feature, we want to add nodes someday, we're going to bind it to the real add node screen runner. This way, all the code that's actually involved in running the add node screen can live in the feature without any dependency. Cool. We also need to move resources, right? When we extract a feature out, all those resources should live in the feature module. Turns out that's not a super easy task in Android Studio, but here's a fun hack you can use. Turn your Android library into a jar. It's really cool, and that just gets rid of all the resources for you. Then from your feature module, just depend on the jar instead of the AAR, and you'll find out exactly all the resources that you're depending on that still live in the spaghetti, because you'll see a lot of compile time errors run in. Then you can F6.
I think you also want to mention the string thing.
Yes, also one of our Android engineers wrote a really cool library for moving strings around, because it turns out it's really hard to refactor and move strings in Android, especially if you have a lot of translation. So Anders, raise your hand, say hi. He's going to introduce an open source library for moving strings between modules in Android, which is something that's actually a lot harder than it should be. Oh, sorry.
Oh, sure. So looking ahead, so we're sort of we went through a bunch of different tools that we can use to analyze and then to actually move things. But then, so you do a nice pull request, you extract a module out, it's merged, you're like happy and excited. And 1 week later, you realize the module was somehow added back. You're like, what just happened? And someone did a mistake. They needed to fix a compiler error. They said, oh, I'll just add this here. And like, all of a sudden, it's back. If you have a small team, that should never happen. But when you have a big team, people don't always know what's going on. And sometimes you need to give them feedback on the PRs that maybe that's not the greatest idea, right? And so it's happened to us, and we decided we need to do something about it. So what we did is we went and looked at some code that Jake wrote for our cache app and reused some of that. So let's go through that. So this is part of our build script on CI. And so on every pull request, we run this. So the first line here captures the size of the APK. So the goal here is to track that over time. And it's not directly related, but there's an indirect correlation. If the APK size grows a lot, there's probably a problem, like someone added a library or a dependency, so we want to know about that. So we track that on every commit. And this is invoking Ruby to, oh, you'll ask Jake, he's over there, he remembers. He told me the reason, but I just copy-pasted. And then the second one is actually pretty cool. So what you're doing here is invoking your unzipping, but without actually unzipping, and streaming that to list all the files and just get a list of the dex files. And this is where it gets interesting. We can iterate over the dex files in the APK. And so you can see that we're reading the bytes of each of the dex files, which is what unzip -p is doing. And then we pipe that into head and pipe that into tail. And so what this is actually doing is taking the first n bytes of the dex file and then removing some bytes, and you end up with a bunch of bytes. And then you use hexdump to turn that into a number, because it turns out that a dex file has the number of classes in its header. So you can just read that out from the dex files. This is what this is doing. But then we realized we wanted more. So we actually decided to unzip the dex file and invoke dexdump to find the list of all classes and put that in a variable. So we do that for all dex files, and at the end of the day, we end up with the size of the APK, the number of classes, and the list of all classes in the APK. Now, what we do is we take these three values and we store them for every single commit that's being built in CI. And that gets interesting. So we can do two things. We push that to a thing called stat-hat, which gives us daily stats, so we can kind of see, okay, this is where this app is, this is where this app is, and we can see the trends. And if a number goes up, we can like, hold on, which pull request was merged, what's going on? But the second thing we did was a bot that automatically posts to the pull request. So this is stash, we use stash at Square. And it posts a comment to the pull request telling you, hey, you increased the class count by more than 100. We just decided 100 is at least something we need to look at. So we're not failing the pull request. We're not saying you can't merge your code, but we're triggering a conversation. We're going to be notified, and then we're like, so what's going on? Why do you need all these classes to be added to this app that we don't, or this SDK that we don't want to have that many classes? And it's been pretty great at detecting these issues ahead of time. And then, once we have that, sometimes it's not enough. Sometimes you look at the diff, and the diff is, I just upgraded the version of this library to +1, you know? Or I just added a small dependency. I don't understand what's going on. And so we also use the list of classes. Because for every commit we have the list of classes, we can do a diff. And then we can figure out, for each pull request, what classes exactly were added in the pull request. And that's pretty exciting, because then we can start looking and we say, oh, right, you upgraded to that new version and they decided to depend on this new library, and all of a sudden you have 10,000 classes appearing. That's happened, so now we're like prepared. So with that, that's kind of like the on the bad cop side of things, but we also have the good cop side of things. We want to encourage people to take things out. So how do we do that? Some people give stickers away. Because I'm French, I like to do crepes, so I just have a Jira and people put their names in there and I just make crepes for them. It's kind of my way to buy people out. It seems to work. And similarly, we have like a bot that's, hey, you just did this great work. Do you want crepes? And then I get notified as well. It's a lot of crepe making. Who's that? This is for you.
Yeah, so what did we learn? We're all dealing with spaghetti code in our day-to-day lives, but we want to build multiple apps on top of that spaghetti code. So we need to figure out how to start extracting it. And we talked about a little bit about static analysis, how that can sometimes work if you're Google Play and you're Jake, and how it can sometimes not work if you're us. It's great if your code's well organized. Not so great when it looks like this, but we can also use runtime analysis to figure out what's running, what's not running, and start making hard cuts.
Yeah. So about the spaghetti code, just to keep in mind, of course we're exaggerating a bit. It's not like all of our code. I don't want people to think, oh, Square has just like a giant ball of spaghetti code. We have some, but like everybody, you know, it's like this code that has a life and has stories to tell. That's how I like to think about it. It's interesting to look into it and do a bit of research. I feel like I'm an archaeologist sometimes. I can look at commits and figure, oh, 5 years ago, this person like did this thing, and that was interesting. So we don't have just spaghetti code, obviously, but we have some, and we're figuring out how to deal with it. The second thing that we want maybe you to remember today is that if you're dealing with that type of situation, you can really think of code as, is it running because it needs to run? Is it running but shouldn't really be running, which is the zombies? There's probably an academic name for it, but we don't know it, so I think zombie is good enough. And then we have the dead code, and the dead code is the code that we want to refactor out. And yeah, so we use runtime analysis to figure those things out. So there's one good news. The more you do it, the easier it gets. That's pretty simple, right? The spaghetti shrinks, and then it's all obvious, and you can just do everything using common sense again, and life is great again. And with that?
That's it. Thank you. Oh yeah, and like PY said, Square is always looking for Android engineers, and it's not all spaghetti.
So we have a bit of time, but if you want to go, you are free to go. And if you want to ask questions, I think we can take a few questions.
Yep.
Go for it. We will repeat the questions, or you can walk up. I think this works. Otherwise, you can shoot, and we'll repeat the question. I'm not sure.
So the question is, are the features combining both UI and business logic in that diagram? Yeah, basically.
Yeah.
And there's a lot of other work going on to restructure our app at the same time. So this is more, I think, about our Android module arrangement and the way we structure everything and how to include it all in the final app. It's not really about separation of UI and business logic concerns, which is obviously really important to have.
Yeah, we are doing more work to separate these two. We haven't really talked about that because at the end of the day, one app probably wants both the UI and the business logic. But we are also like splitting sideways between business logic and UI.
But similarly, if you want to include a feature in an app, right, you probably want neither of the two, right? So we should split out both the UI and the business logic, but they don't have to necessarily be in the same module either.
Yeah. All right, I think that's it. Have a good day. Thank you.